All right. Hello, everyone, and welcome to the afternoon session. I think we'll get started. The first speaker of the afternoon session is David Dunsky from Berkeley, and he's going to tell us about gravitational wave gastronomy. So, David,
okay.
floor is all yours.
Yeah, thank you. Yeah, and thank you for the organizers for the opportunity to talk. I wish I could be here with you guys in person. Unfortunately, I got COVID last week, so I'm doing things from afar. Thank God for Zoom still. What I want to talk a little bit about is some gravitational wave gastronomy. And this is some work done with a few other gastronomers, Anish Ghoshal, Hitoshi, Yuki Sakakihara, and Graham White. And so you may be asking, what in the world is gravitational wave gastronomy? So if you look up in the dictionary, you won't find a definition. So we have to come up with a few of our own. So very basically, it's just a savory variation of gravitational wave astronomy. A little bit more concretely, it's the search for gravitational wave signatures from the eating of one topological defect by another. And it's observed to occur in hypertopological defects like domain walls bounded by strings and strings bounded by monopoles, which I'll talk about quite a bit in this talk. And what's really cool is it's seasoned with some equal parts of gravitational wave physics, early universe cosmology, and grand unification. So for the beginning, the appetizers, I'll talk a little bit about, so very basically just some gravitational waves as probes of the early universe and their relationship to guts. Some of the motivations I know we're very familiar with those, so I'll just kind of briefly go by those. And then for the entree, the main part, I'll talk a little bit about the dynamics and the gravitational wave signatures from these hypertopological defects. And for the conclusion, for dessert, I'll talk about how we can use these gravitational wave signatures and how they're related to grand unified symmetry breaking chains, and maybe they can be used to distinguish various grand unified symmetry breaking chains down to the standard model. Okay, so just to begin with, gravitational waves are really pretty awesome because they're pretty amazing probes of the early universe. So we know like electromagnetic waves are opaque to time scales before 300,000 years, right? Before recombination, temperatures of order an electron volt. Whereas gravitational waves are unimpeded by the primordial plasma. It can just travel basically unimpeded from very early times to today. And because very early times and very high temperatures correspond to very, very high energies, we can potentially use these gravitational waves to probe energies far beyond current and near future colliders. So they really offer a remarkable probe, a remarkable window really into the very early universe. The key thing is that you need a source of gravitational waves in the early universe, right? And this is where grand unified theories come in. So we think that the true symmetries of nature are restored at very high temperatures in the early universe. And as the universe expands and cools, right, the fundamental gauge group of the universe breaks down to the standard model. So this is in contrast, of course, to colliders, where we start with the standard model gauge group and we try and work our way up to higher energies to figure out what this gauge group G is. Now, for many of these symmetry breakings, many of these gauge groups actually leave behind relic topological defects if they have a non-trivial vacuum as characterized by the homotopy group. So for homotopy group pi 0, where this d is equal, pi 2, when this d is equal to 0, you can get magnetic monopoles form. For big D equals 1, you can get the kind of the one-dimensional analog cosmic strings. And for big D equals 2, you can get the two-dimensional analog, these domain walls. And the key ingredients that these topological defects have is that they're generally quite massive, right? Because their mass scale is typically set by the symmetry breaking scale that form them. And they can accelerate to very relativistic speeds. And so that combination of like those two ingredients are really what's necessary to get a very powerful source of gravitational waves in the early universe. So these topological defects can provide that source of gravitational waves that we can use to detect today and potentially infer information about very fundamental physics. Now, what's pretty interesting is that for some of these chains, you can actually get hybrid topological defects to form. That is, for instance, you can get strings bounded by monopoles or walls bounded by strings. So for instance, like for the first case, typically arises in the following scenario, where you have some gauge group G, gets broken down to some gauge group H with some additional U1 factor, which will give you magnetic monopoles. Now, when this same U1 is broken, what happens is these magnetic field lines of these monopoles basically squeeze into flux tubes connecting monopole pairs. And the flux tube is what the cosmic string is. So that's how you can get monopoles bounded by, or strings bounded by monopoles. A very similar thing happens for the kind of higher dimensional case. It kind of typically arises in the following scenario, where you have some gauge group G gets broken down to some gauge group with some discrete symmetry that's associated with the string. Now, when this same discrete symmetry is broken, the breaking of that discrete symmetry will produce a domain wall. And that domain wall will actually be attached to the cosmic string in a similar manner to how the magnetic field lines get squeezed into these flux tubes for the monopole anti-monopole pairs. And in both cases, excuse me, what happens is that you get a tension force. You can think about, for instance, the string tension on the magnetic monopoles causes relativistic oscillations, or the wall tension on the string causes relativistic oscillations of this various hybrid topological defect. And that relativistic oscillations can produce gravitational waves and cause a system to decay. Another way to think about this tension force is equivalent to converting basically rest mass into kinetic energy. That's the eating process, this gastronomy that we're talking about. So for instance, you get rest mass conversion of the string into monopole kinetic energy, causes the motion, this relativistic motion of monopoles, or the rest mass conversion of wall rest mass into string kinetic energy gives you very relativistic string boundaries. And as I said, that this relativistic oscillations and movements can cause very strong gravitational radiation. And the name of the game is to find what kind of signal that these hybrid topological defects produce, and can they be used to fingerprint, for instance, these type of grain unified theories that produce these patterns. And just to give you an example, that these patterns are actually quite ubiquitous, or these hybrid defects, I should say, are quite ubiquitous in many symmetry breaking chains down to the standard model. So for instance, here's an example of some SO10 chains down to the standard model 321, where red lines correspond to magnetic monopoles, blue to strings, green to domain walls. Excuse me. So a red glowing path corresponds to strings that eventually become connected to monopoles, whereas a blue glowing path corresponds to strings eventually get connected to domain walls. So kind of an example for a gauge group that you get monopoles bounded by strings is one that Kai was talking about earlier this morning. So for instance, if you have some, GSM with some extra U1, if that U1 gets broken, you can get, if you have SO10, or for instance, 3221 gets broken down to some extra gauge group with an extra U1, then you can get magnetic monopoles. And so if that U1 is later broken, you can get the monopoles become attached to strings. So that was kind of the example that Kai was talking about a little bit earlier today. But you can get, for instance, walls connected to strings. For instance, if you have, say this 3211 gets broken down to 321 cross Z2, where that Z2 is arising from the center of this U1, well, that produces cosmic strings. And if that same Z2 symmetry is later broken, you get domain walls, and those domain walls know about the strings and they become connected, and you get walls bounded by strings. So these are actually quite prevalent in many SO10 symmetry breaking chains down to the standard model. So what I'm going to do now is I'm going to talk kind of about the four-course menu of different hybrid topological defects that you can get in the typical gravitational wave signatures that you can get from them. And so there are really two kind of cases where you have monopoles connected to strings, or strings connected to domain walls. And then you have, depending on when inflation occurs relative to the formation of the defect, gives you four total different unique signatures. And so the first one I'll talk about briefly, because Kai basically talked about it earlier today, is a case where you have monopoles eating strings. That is a nucleation of monopoles on strings. And they occur in basically the following scenario, where you have monopole formation, and then you have inflation, where you dilute all your monopoles. And then you have strings form. So that U1 associated with the monopoles is broken, and you get strings form. But there are no monopoles around. So the strings can't attach to any monopoles. So they just behave like a normal string network. They have no idea that there are monopoles around them, because there aren't any. They've been inflated away. And if you wait long enough, then it becomes probabilistically favorable and energetically favorable, where you can actually convert string rest mass into two magnetic monopoles. This is a nucleation of the monopole pairs on the strings. And then the tension of the string, or equivalently, the rest mass of the string will get converted to monopole kinetic energy, causing this relativistic motion and decay via gravitational radiation. So before the nucleation occurs, the strings just act like a normal string network. And if the gravitational wave signal that you get is just a normal, typical flat string spectrum at very high frequencies corresponding to early times. Eventually, if it becomes energetically favorable, which is set roughly by the monopole mass squared over the string tension, if that's kind of close enough, that ratio is relatively small, it becomes probabilistically favorable within cosmological timescales to nucleate monopoles and destroy the string network. And those occur at late times or equivalently low frequencies, because the scale of the system of the strings are very large then, so the frequency is very small. And the whole network decays, and you get an F squared IR power law. And so this can, since it occurs generally, it can occur quite late cosmologically at very low frequencies. You can potentially use this to detect, or for many parameters of the strings and monopoles, you can detect in near future gravitational wave detectors. So I'm going to talk a little bit briefly now about kind of a higher dimensional analog of this, which is strings nucleating on walls, that is, strings eating the walls. So this is basically just the higher dimensional analog of what I just said, which is what Kai was talking about more in depth this morning. And so the case, kind of the scenario for this to occur is you get strings form, and then you have inflation, so no more strings around. And then you have some discrete symmetry associated with those strings gets broken, and you get domain walls, but there are no strings around, so they can't attach to any strings. And you get a normal domain wall network that evolves like a normal, just regular domain wall network. But again, if you wait enough time, it becomes energetically and probabilistically favorable, where you can actually remove wall rest mass and convert into a string. This is a nucleation of the string on the boundary. And moreover, it's further energetically favorable for the string to expand. And it's actually like a relativistic rocket where it eats the wall rest mass into string kinetic energy and expands, and it eats the wall, and the whole network decays. So before the string nucleates on the wall, it just acts, the wall, it just behaves like a normal domain wall network that eventually will reach scaling. And simulations have actually calculated what the gravitational wave signature looks like of just a stable domain wall network, or at least one that is stable before decaying, for instance, by adding some discrete symmetry breaking. And in that case, what happens is the signature, the frequency dependence, is kind of like a triangular shape, where in the UV, it's f to the -1, and in the IR, it's this causality f cubed that Anson talked about yesterday. And the longer this wall lives, it actually, this omega gravity wave grows in time, unlike the strings, which are flat. And the reason it just grows in time is that the energy density of the wall network grows relative to the background, and it'll eventually dominate, of course, the background. That's just a domain wall problem. So you can't actually have these walls live too long because they'll eventually come to dominate the energy density. So if a hierarchy of scales between the string tension and the wall tension are close enough, then the nucleation probability can be probabilistically of order 1 in cosmological timescales, and you can get the whole wall system to decay before coming to dominate the energy density. But you do need like a hierarchy of scales for this to occur. But this is a typical spectrum that would be expected to be seen. And again, it's different in the IR and in the UV than the nucleation of monopoles on strings. So for the last, I guess, 5 to 10 minutes or so, I'll talk about a little bit more in depth the last two cases, which are strings eating monopoles and walls eating strings, which occur in the exact same symmetry breaking scale, symmetry breaking patterns as before, as these blue highlighted cases do. But it just differs when inflation occurs. In particular, inflation occurs before all these defects occur. So there's no nucleation. The strings will just eventually attach to the monopoles, or the walls will just attach to the strings. And you can get actually different gravitational wave signatures from that, although they are typically, as we'll see, more in the ultraviolet frequencies, or very, very high frequencies. So, so for instance, the case where strings eating monopoles, this collapse case, occurs in the following scenario, where you have inflation first, and then monopoles. So monopoles don't get diluted, but they do freeze out a little bit. So their number density does drop just a little bit. And when that U1 that's associated with the monopoles breaks, Again, those magnetic field lines get squeezed into flux tubes, which are the strings. And the typical length of the string segment is of order 1 over the cube root of the number density of monopoles at string formation. And so now you have you can't have relativistic oscillations of the monopole anti-monopole pair before the whole just monopole string network just decays via gravitational radiation. And so I'll just talk a little bit about how you can estimate this. We actually do the computation a little bit more rigorously, but just to estimate this, it's very simple, and you can apply this to kind of many stochastic signals. And what you do is you just calculate first the energy density deposited in gravitational waves produced by this burst of monopoles connected to strings as this brief oscillation before they annihilate and decay. Excuse me. So the way you can do this is just take the number density of monopoles at the string formation scale, multiply it by the power emitted in their gravitational waves, times the lifetime of the monopole string system, which is actually generally quite short because it actually will generally decay from scatterings with the plasma too. That's an extra branching ratio, if you will. So that actually sets what the lifetime is. But the power in the strings, in the monopole string system is actually roughly just g mu squared, has been calculated by others. And the reason it's just g mu squared, which is typically the normal string loop power, is because the energy source of the monopoles is coming from the string. So that's basically just setting the power and gravity waves. So just taking this rho gravity wave, normalizing it to the background density gives you roughly what you expect the amplitude and omega gravity wave to be in this burst. And the frequency is roughly set by the length of this monopole string system, which is actually quite small because it occurs in the very early universe at the string formation scale. And so here's just a typical plot of what the more rigorously calculated spectrum looks like for various parameters, the monopole and string symmetry breaking scales. And you can see that it's actually generally quite low omega gravity wave, but more importantly, it's at very high frequencies. And so this is actually quite hard to detect at the moment, though we heard talks earlier about potentially detecting very high frequency waves, gravity waves, but more work will need to be done to reach these low omega gravity waves. But if they can be detected, you can actually see a different frequency dependence compared to the previous hypertopological defects. Okay, so I've got just a couple minutes left. So how much time do I have left? So I'll probably go through the last part.
Around 5 minutes.
Around 5 minutes? Okay, cool. So I'll briefly go over this last part of the last course. The final course is walls eating strings. And it occurs in the following situation, where you have inflation first, and then you have strings form. And these strings evolve like a normal string network. Eventually, when the Z2 symmetry that's associated with the strings gets broken, you get domain walls form, and they will come to fill in the strings. And this wall string system will eventually collapse. And what actually happens is there's a new scale that enters the problem, which determines when this wall string system collapses. And very simply, you can estimate it by just comparing the string force and the domain wall force and seeing that there's a given radius, roughly the ratio between the two tensions of the systems, of the string and wall tension, where wall string systems that are greater than this critical radius, are dominated by the wall, which will cause the wall rest mass to convert to string kinetic energy and eventually collapse. Or when the string wall system is less than this size, the string is just dominating the dynamics and you just get a normal string system. So I'll quickly just say that we can more rigorously compute this with just calculating the Nambu-Goto action of a wall and a string, with the identification that the domain wall, the boundary of the domain wall, is the string, is a string boundary. And what we can show is that we can compute for a circular wall-bounded string case semi-analytically and numerically what kind of the oscillation motion of this wall string system is. And basically what you find is that for string wall systems that are much less than this critical radius, they oscillate just basically like a pure string loop, which is this dashed blue curve. As this radius of the wall string system grows, the walls become more important in the dynamics of the wall string system and dominate, that is, they dominate it and cause very relativistic motion of the string boundary. So we can apply this to the string cosmology. For instance, the infinite string wall network, which breaks off and forms these string wall loops. And effectively what we find is that exactly that this critical radius is very important. by solving a one-scale model, which is what's typically done for just pure string loops, or pure string networks, which is basically an average Nambu-Goto equation of motion. And we find that for walls that enter, or the domain wall formation time that is before this critical radius, the string wall network evolves as just a pure string network until it grows and grows in size. And basically, when the horizon size becomes of order this critical radius, what happens is the walls pull the strings in to the horizon and cause the string wall system to collapse and oscillate at constant size before decaying via gravitational radiation. If, however, the domain wall formation time is greater than this critical radius, then the walls, when they form, dominate the strings right at formation. And the string wall system will still collapse into the horizon, but it just gets even more relativistic very, very quickly. So once the wall string system is in the horizon, you can estimate what the power emitted in gravitational waves is. And very simply, we can actually do an estimate for using just a quadrupole formula, the analogous kind of Larmor formula for gravity waves. For a string case, you would think it's just g mu squared from the quadrupole formula, while for wall-dominated case, you get g sigma m. Now, what happens in our string wall system? Well, numerically computing this, which is just doing basically the Fourier transform of the transverse traceless tensor of the string wall network, is that when the string size is much less than the critical radius, we get precisely the expected power from a pure string loop. Whereas as a string wall system grows in size, you get the g sigma m limit, which is just a pure domain wall case. And this is expected because that's where the energy of the string is coming from, is precisely from the domain wall energy, the domain wall rest mass, because that gets eaten by the string boundary. So just last, I'll just show you the plot of a typical gravitational wave signal from these string wall systems. So when the domain wall formation time is below R critical, the string network just acts as a pure string network. It's flat. And once the size of the string wall system grows above RC, the network will collapse as F cubed. Whereas if the domain wall formation time is actually above the critical radius, as shown here, for instance, you can actually get a little bump in the spectrum before it decays because there's more energy density actually in the system, or it takes longer for the wall system to decay in that case. So just an overview of this 4 spectra is that each of this 4-course menu of strings attached to monopoles or walls attached to strings, and when inflation occurs, gives actually rise to different IR and UV features in the frequency spectra. And excuse me, in conclusion, basically, these gravitational waves can really provide a pretty amazing view into the early universe. And it may be possible that we can detect, or if we can detect some of these gravitational wave signals, we can use those to fingerprint what kind of symmetry breaking chains occur and understand the universe at a really fundamental level. So the future is very exciting, and thank you.
So thank you for the wonderful talk. We'll take questions. Yeah.
So in the first 2 cases, monopoles eating strings and strings eating domain walls, the 2 scales had to be very close to each other. The monopole and string, or string and domain wall. Means they have it closely in time. Does that leave you enough time for dilution? Or like, can you actually use the proximity of the scales to put a bound on how much dilution that can happen, or they're completely irrelevant?
Yeah, you mean like dilution from inflation, for instance?
That's right. How big of an inflation can you have?
Yeah, so it's a good question. So I mean, the symmetry breaking scales that are associated with the wall and the string case, for instance, or the strings in the monopole case, are related, of course, to the actual the tensions, which actually enter into the ratio of the probability of nucleating. So, for instance, for the strings in the monopoles, what enters is kind of an e to the minus monopole mass squared over the string tension. So those string tensions in the monopole mass are not quite exactly the same as a symmetry breaking scale, because there's some coupling constants that enter, for instance, but they're generally pretty close. So you can fiddle around with the difference between the tensions and the symmetry scales a little bit. But I'll say for the monopole and string case, you have more of a hierarchy you can have between the monopole formation scale, inflation, and then the string scale, than you can with the domain wall in string network. And the reason is because the that exponential that enters that I just said, for it to basically become of order 1 within 13 billion years, you can have that ratio between m squared and the string tension be, I think, something like 60 or something like that. So you can have actually a decent hierarchy, not that large. It's worse though for the walls in the strings, because what enters in there is again an exponential factor for the nucleation, as you said, but it's a higher power of the symmetry scales. Basically, it's to the 6th power, roughly speaking, in the symmetry breaking scales. Again, there is some fiddle, like there's some room you can fiddle with between the tensions and the actual symmetry breaking scales, but those have to actually be even closer together. So it's difficult, but I haven't worked on a model, but it potentially is possible to stick in to sandwich inflation in there, but it's much more difficult for the walls and string case. I think it could be done with the wall, with the string and monopole case, because you can have a larger hierarchy and still get a signal.
I guess what I'm asking is that is the number of e-folds you can have is related to the hierarchy of the scales or no?
Yeah, so the number,
yeah, also determines the dilution factor.
Yeah, so for the inflation, so I'm just assuming that the walls, like if inflation occurs, what I assume is that the walls will never be able to find another string within cosmological timescales, or the strings will never be able to find a monopole. Technically, if you have, for instance, some like if the number of e-folds is not that high, like you have some other dilution, not necessarily inflation, what happens is that eventually when the strings get bigger enough, they can become attached. They'll eventually find the monopoles, and you can get the whole system to collapse then. But the number of e-folds that's required, I don't know off the top of my head. But I mean, is that what you were asking? I guess.
Yeah, but
yeah.
It's okay.
Okay. We have another question in the audience.
Okay.
Yeah. So I have a question and a comment. Can you hear me well?
I think I can hear you. Yeah.
Yeah. Okay. So the question is related to the previous one. So in the case of the nucleation of either monopole or whatever, so it appears to me that there is a quite strong fine tuning
Right.
that you need to do in order to have this in cosmological times. So if you were to translate this condition of this in order for this tunneling separation factor into the non-unification parameters, I would expect it would be a very thin region in parameter space where you can organize for it, right?
Right. So the tuning, you're right. So there is, in some sense, a tuning in that you need these scales to be relatively close, and not only that, you need inflation to sandwich in between them, right? For the nucleations. For the string monopole case, which I show here, for instance, like the tuning of like how close you need the scales to be is not like too severe. So you can get, for instance, like an order of magnitude hierarchy difference between roughly the two scales, between the monopole and the string symmetry breaking scales, roughly speaking, and still get an observational signal and a difference between a completely stable string spectrum. For the domain wall case, it's trickier because the hierarchy has to be even closer together, because the power is a little bit stronger. But I mean, you can still do it. And I guess it's maybe more possible or more likely in the string monopole case, I would say. I mean, yeah, but there is tuning for sure that enters into this, so you get the decay.
So then, in connection to this, just the comment is that there's another class, quite a big class of models that realizes also a hybrid of defects, where some of these issues are served, which is in axiomic models, where you have for sure the strings that are then eaten by the domain walls. You see the isotopes here, and so that's not by nucleation, but just a further symmetry breaking.
Mm-hmm.
And that case actually, yeah. So if you consider,
I couldn't hear the last part, but you're talking about axion hybrid defects. Is that right?
exactly, yes, yes.
Yeah. So
It's also
yeah. So I mean, some of this analysis does apply to global defects or global hybrid defects, but the issue with those defects generally is they can decay by emitting pseudo-Goldstone bosons, not just gravitational waves. So that changes the lifetime of some of these defects and changes the gravitational wave spectrum. But we didn't consider global hybrid defects, but some of the analysis applies to them. It's just kind of there's an additional decay channel often for these, and that changes things a little bit.